Welcome back. We are still looking at section 11.9. This is the last video. I just wanted to show you a neat example here and talk about the integration and differentiation of power series. Power series are the noticed functions, or function can be represented by power series. So if a function is differentiable, and when is it differentiable? When it is continuous. So if the function is continuous, it means the power series is continuous, and then also they are differentiable and they are integrable, like the functions are. Okay, so we saw a few examples here of how to write a function of a certain form using the geometric series concept or format. We were able to write down the power series for some functions. Now here are two examples for you to try, which you should be able to do them, and I think there shouldn't be an issue with that. So let's now look at a little bit deeper into the power series and differentiation and integration of the power series. So we have that if we have a power series sigma n is equal to 0 to infinity Cn x minus a raised to the power n, and it has a radius of convergence which is positive, r is greater than 0, then the function f of x equals, so let's expand it, because the differentiation and integration we are going to do it term by term. We can do it directly, but we might lose some terms if we try to do it on the closed form. So this is the closed form, this is the open form. So we are going to look at the open form, and then we are going to integrate and differentiate. So looking at this one, if I want to differentiate, then f prime x will be equal to, now derivative of c naught will be 0 because c naught is a constant, plus c1 into derivative of x minus a, which is 1, because we are differentiating with respect to x. So we get c1 plus, so c1 from here, and now when I differentiate this one, c2 is constant, so it stays there, but the derivative will be 2 times x minus a raised to 1, or 2 times x minus a. So our second term comes out to be 2c2x minus a, plus, now the next term is going to be c3 x minus a whole to the third. So when you differentiate this quantity, you will get c3 times 3x minus a whole square. So that is what I have in here, 3c x minus a whole square plus so on and so on. So now if you convert it into, write it in the closed form, it will be like this. Summation n is equal to 1 to infinity. 1 to infinity. Note that. Not 0 to infinity. Although the function was starting at n is equal to 0. But the derivative is starting at n is equal to 1, because we have one of the term, one power has gone down. So that, and then there is a number n being multiplied with each term. If it's the second term, we have a 2, third term we have a 3 being multiplied, and so on. So we have n cn x minus a raised to the power n minus 1. Why n minus 1? Because see here, this is the second term, but the power here is 1, so 2 minus 1. This is the third term, 1, 2, 3. So third term we have 3c3, but the power on x minus a is 2, which means n minus 2. Sorry, n minus 1, and so on. So this is the compact or the closed form of the derivative. Now in the same way, now we can anti-differentiate or take or integrate or find the integral. So integral of f of x dx will be equal to, now you know the how to integrate term by term, but you know we will have a constant of integration. So usually we put it at the end, but now let's put it in the beginning because we see our function is in increasing order. So the first term I write is the c, the constant of integration, plus c sub 0, c naught, which was a constant, so it will be multiplied by x in our usual sense. But you know we can easily say x minus a. Why? Because the um, the extra term that we get when we expand the first term, it gets absorbed into the in the c, the constant of integration. So we have c sub 0 x minus a plus c sub 1 x minus a whole square over 2 plus c 2 x minus a whole cube over 3 plus dot dot dot. Okay. So here the sum will be actually is equal to 0 to infinity. Why 0? Because you see the c sub 0 here. See, we didn't have the c sub 0 here, so we, it didn't make sense to start the series at 0. So in this case, we have a c sub 0, and so if we start at 1, we will miss the c sub 0. So we have summation n is equal to 1 to infinity Cn. So Cn just stays there. Now this time we are not getting a n, or a factor of n as a multiple, but we are getting it in the denominator. So x minus a raised to n plus 1 over n plus 1. Now it looks like, see, this is your given series. It looks like we can just say derivative is, we get, as if we are just differentiating this thing inside, summation Cn times n x minus a raised to n minus 1. But then we could have the problem with the n. That's why it's better to differentiate or integrate and on the open form. Okay, now let's look at the one example here. It says find a power series for function g of x is equal to tangent inverse x. So we notice that the derivative of tangent inverse x is 1 over 1 plus x squared. But what is this? We have seen this recently. I think in video 1 I showed you how to write the power series for this function. So when we can use the power series for this function, and in order to find out tangent inverse x, we will have to integrate the quantity 1 over 1 plus x squared dx. So that's what I'm going to do and show you here. Tangent inverse x will be equal to integral of 1 over 1 plus x squared dx. Now in this form, we will expand. So we have 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8 minus x, and so on. This is what we saw the power series of 1 over 1 plus x squared gives us. So now we integrate So c plus, so the 1 will become x, the x square will become x cube over 3, so minus x cube over 3, then plus x to the 4 will become x to the 5 over 5, and x to the 6 will become x to the 7 over 7. So we are getting now odd powers of x plus so on. Now to find c, we use the fact that tangent inverse of 0 is equal to 0. So when we plug in 0 on the left hand side, we are going to get 0 because tangent inverse of 0 is 0. So that on the right hand side, we get we will get all zeros except for the c. So left hand side is 0, so which means c is 0. Because we are getting 0 equals c plus 0 plus 0 minus 0 plus 0 minus 0 plus 0. So eventually this is going to give us c is equal to 0. So that tangent inverse x can be written as x minus x cube over 3 plus x5 over 5 minus x7 over 7 plus x9 over 9 minus x11 over x to the 11 over 11 and so on. So this is tangent inverse x. Now people have been using this expansion in order to find the digits or the decimal places of pi, for a long time. So to have very high power of pi. So this is just was an example I wanted to show you. This is kind of a application of the power series. Okay, that's all for section 8.11.9.